This problem says find the limit if it exists. So here we are, we've got a quotient of polynomial type functions. And we can see that if we just proceed to plug in x, the denominator is going to go to 0, which is undefined. So first of all, what would you do? Would you try to use a limit theorem right here, such as the quotient? You know that the limit as x approaches some value c, say the top function is a function f of c, and the bottom function is a f of x, I should say. And the bottom function is this immediately usable? What are the restrictions on this? Oh, that this is equivalent to the limit as x approaches c of f of x over the limit as x approaches c of g of x. This is not immediately applicable because what is the rule about this? That the limit as x approaches c of g of x does not equal 0. It needs not to be, the limit needs not to be 0. And so sometimes you have to be careful before you start charging and using these limit theorems. So what we should do is see what this factors out to. What is x? What is the difference of this? I mean, what is x minus 2 squared equivalent to? We can rewrite that denominator as this. And what we should try to see is if the numerator also has an x minus 2 factor. First of all, let's write this. Okay. Now, x squared minus x minus 2. Have you ever learned this technique, which sometimes has a solution, sometimes not? First of all, we know that x squared has a coefficient of 1, so I just put x and x. And these two terms will have to multiply out and equal -2 when you multiply them. And if you can find two terms that multiply to equal the third term and add to equal the second term, and after a whole lot of doing these types of problems, you can start to figure it out in your head. So if I do this, you see -2 times +1 is -2, and -2 plus 1 equals -x. So this is equivalent to x minus 2 over x plus 1. So after that, since we don't worry about the limit at x equals 2 existing, we can cancel out an x minus 2 on top and an x minus 2 on bottom, but that leaves us with is there any way to prevent the denominator from going to 0? Not that I can see. In fact, as you look at a graph of this, here's, let's say this is 2 and this is -1. Let's do a little bit of function graphing. I'm going to put some positive and negative marks along the bottom that represent the sign of this denominator function. We know that for values less than 2, this is going to be negative, so I do this. And at 2, we know this whole thing is undefined because 2 minus 2 is 0, and a 0 division is undefined. But once we're greater than 2, oh, let me put this down here because this is down low, the denominator. Now the top function, x plus 1, is negative for values of x less than -1. And it's 0 at -1. And it's positive for everything greater. So we can see that this is positive and this is negative. So this function is going to be getting more and more negative at this point. But once it's slightly larger than 2, it's going to be very large in the positive infinity direction. So you can see there's no value of L here. Remember the definition of the limit? There's no value that as you get closer to 2, this does not converge, because right before 2, it gets larger and larger in the negative infinity, and right greater than 2. So we can say that this limit does not exist. You could prove it more formally using the definition of the limit. But in this case, using the limit theorem to turn it into a quotient of limits still did not make a limit exist. So we can say that there is no limit for this particular function. This problem says find the limit if it exists. The limit as x approaches -2 of the square root of x squared minus 4x plus 1. So this is a point where we can use a limit theorem that states basically the limit as x approaches c of the nth root of some function f of x is equal to the nth root of the limit as x approaches c of f of x if the n is a positive odd number and the limit as x approaches c of f of x exists. I'm just going to write limit exists, meaning this inside. Then you can use this theorem. Now if n is even, then not only does the limit as x approaches c of f of x need to exist, it needs to be non-negative. It could be 0 or a positive amount, but if it's negative, then you can't say that this is equal to this. First of all, let's look at this. Basically, when there's no number shown, we know that that's the square root where n is equal to 2. So now we need to find out if the limit of the function as x approaches -2 of x squared minus 4x plus 1 exists and is non-negative before we do the taking out of the square root outside of the whole limit. And here we are. We've got this. Now we can use some more limit theorems, basically the sums and differences. The limit of a sum you can go through and find a proof of this, which is good to do at least once in your life. We know that the limit of a sum of functions, as long as the following exists, this is okay. We can take the sum of the limits. We can find the limit as x approaches c of f of x. Then we can add it to the limit as x approaches c of g of x. So in this case we have 3 addends, but we can extend the sums and differences. So we can say that this is the equivalent to the limit as x approaches -2 of x squared minus the limit as x approaches -2 of 4x plus the limit as x approaches -2 of 1. Now we've got these 3, and the proof that for a constant function, where this is the function, this is the x and y axis, if a function is 1 everywhere on the real number line, -2, and everywhere else, then the limit of this one is going to be 1, because it's 1 everywhere. There's also a proof that for a constant times a value, there's this limit theorem. We know that the limit as x approaches c of, let b be some constant number where b is a real number, and f of x is some function. In this case, when you're multiplying a constant by a function, you can take the constant outside and say that. So that means that we can turn limit 4x as x approaches -2 to 4 times the limit as x approaches -2 of x. Now we can use another limit theorem that states that for the identity function where f of x is equal to x, the limit as x approaches -2 of x is equal, we're stating the general case where x approaches c, where c is any real number value, is equal to c. Obviously, you can formally prove this, but, you know, if the function and so on, we know that at -2, the function x approaches -2. So put that all together. That means that this is equal to 4 times -2, which is -8. Now this squared function. We have a limit theorem about exponents, positive integer exponents. It turns out that there is a theorem that states that the limit as x approaches a, where a is some real number, of x to the nth, where n is a positive integer. Later on we can show how it's also true for rational exponents. There's a theorem that states that if you take the limit as x approaches a of x to the nth, you can take the exponent outside of the limit. This is sometimes stated: the limit of an exponent is an exponent of the limit. So this means that we can say that this is the limit as x approaches -2 of x squared. And we just used the theorem that states that this inside the parentheses is -2. And what's -2 squared? It's equal to 4. So now this is 4. 4 minus -8 plus 1 is 4 plus 8 plus 1. That means that this equals 9. Now we can go back and say, is that limit theorem involving roots applicable? This is a 2 because we're talking about the square root. So it's even. So the stuff inside has to be a positive limit. It is. That means that we can say that this is equivalent to the limit as x approaches -2, the square root of the limit as x approaches -2 of x squared minus 4x plus 1. And we just proved that this is 9. So the square root of 9, the answer is 3. And this one says find the limit if it exists. The limit as s approaches 4 of 6s minus 1 over 2s minus 9. So with this one we can use the quotient theorem for limits, but we have to make sure of something first. But the quotient limit theorem was that the limit of a quotient of two functions is equal to the quotient of the limits if the limit of as x approaches c of g of x must not be 0. It must not approach 0. Otherwise, the limit does not exist. Okay. Let g of x be 2s minus 9. What is the limit as s approaches 4 of 2s minus 9? We can start to do this more quickly once we know the constant limit theorem, that the limit, that this is the difference of the limit of this minus the limit as s approaches 4 of this. And we know that this is a constant function, so the limit is just going to be 9. We remember the theorem that the limit as s approaches 4 of 2s would be the same as 2 times the limit as s approaches 4 of s. And we know the identity theorem that the limit as s approaches 4 of s is just going to be 4. So we have 2 times 4 is 8. 8 minus 9 is -1. And that's nice because it's not equal to 0, which means that we can apply the quotient limit theorem that we just spoke of. So we already know that this is going to be equal to the limit as s approaches 4 of 6s minus 1 over, and we just figured out that the limit as s approaches 4 of 2s minus 9 is -1. And solving the limit as s approaches 4 of 6s minus 1, you know which ones to apply. What do you think the limit is? Can you basically already plug in 4? 6 times 4 is 24. 24 minus 1 is 23. 23 over -1 is -23. This problem says find the limit if it exists. The limit as h approaches 0 of 9 plus h to the -1st minus 9 to the -1st over h. So try pausing this video and solving this one if you know the technique that you want to use. So given the quotient theorem for limits, is it possible right now to convert this into a quotient of limits? No, right? Because this limit we know is going to be equal to 0. So that means that we have to leave this as a single function which has a quotient right now. So where do we start? We can't use we can't really do a binomial expansion on a negative exponent. So what could we convert this into? How about this? It's still the limit as h approaches 0, and in the denominator we still have h. What can 9 plus h to the -1st be converted into? You remember what the definition of a negative exponent means. It means the reciprocal of. Let's do the same right here. 9 to the -1st is just 1/9. So now we have this. And we still can't convert this into a quotient of limits. And since this top isn't a limit function by itself yet, we cannot bring the limits into here. So what we can do is combine this fraction, right? Let's rewrite. I'll just write the denominator. Okay. So 1 over 9 plus h minus 1/9. We need to have a common denominator. We have 9 plus h and 9. So let's just write this, 9 plus h. So we multiplied this by 9 over 9. and minus, and we multiply this fraction by 9 plus h over 9 plus h. Now make sure you put these parentheses right here. Okay. So now we have this divided by this and all of it divided by this. What we can do is bring this up here, right? So we have the limit as h approaches 0 of, now it's all just a single fraction. On the numerator we have 9 minus the quantity, 9 plus h. And in the denominator we can put 9h times 9 plus h. Okay. What should we do to the numerator? Yes, we should get it into us without the parentheses. So this is the limit as h approaches 0 of 9 minus 9 minus h over 9h times 9 plus h. 9 minus 9 is 0. 0 minus h is negative h. So this is the limit as h approaches 0 of negative h over 9h times 9 plus h. What can we cancel out now? What do we have in both the numerator and the denominator? Finally, we can get rid of this h, which leaves us with the limit as h approaches 0. There's just a negative up top, so we can just put negative 1. 9 times 9 plus h. Now we can apply the quotient theorem of limits. We can say that the limit of this quotient is equal to the quotient of limits because as h approaches 0, this function does not approach 0. So now it's okay to turn it into this. Now, if we want to, we could convert this limit of a product into a product of limits because we have that limit theorem. And then this term, this factor right here, 9 plus h, could be converted into a limit as h approaches 0 of 9 plus a limit as h approaches 0 of h. But since we can see that this limit is approaching 81, you see as h approaches 0, it just becomes 9 times 9. And this top one is a constant function. The limit as h approaches 0 of negative 1 is negative 1 because the function negative 1 is negative 1 everywhere, no matter what h is. So we finally come at the answer of negative 1/81. I think the most important thing to remember is not to apply the quotient theorem of limits until you have a function whose limit is not 0 in the denominator. That's why we had to do some algebraic manipulations first. This problem says find the limit if it exists. The limit as x approaches 1/2 of 2x squared plus 5x minus 3 over 6x squared minus 7x plus 2. There's a theorem about rational functions, which are quotients of polynomial functions, that says if the polynomial in the denominator does not equal 0 at the given limit, then the limit of the rational function is the value of the function at the limit. But unfortunately, if you plug in x equals 1/2 to 6x squared minus 7x plus 2, you find that it does equal 0 at that point. So you can't use the rational limit theorem. So since the denominator polynomial equals 0 at x equals 1/2, we need to figure out how to factor out an x minus 1/2, which is the same as 2x minus 1 from both the numerator and the denominator. As we've done here, I've factored out a 2x minus 1 from the denominator, and it turns out 6x squared minus 7x plus 2 is equivalent to 2x minus 1 times 3x minus 2. Now, if we divide 2x squared plus 5x minus 3 by 2x minus 1, 2x times what equals 2x squared? X. Okay? 2x times x is 2x squared. X times -1 is negative x. 2x squared minus 2x squared is 0. 5x minus negative x is 5x plus x, which is 6x. Drop the minus 3. Now, 2x times what is 3? 6x? 3. Positive 3. 3 times 2x is 6x. 3 times -1 is -3. 6x minus 6x is 0. And 3 minus -3. -3 minus -3 is -3 plus 3, which is 0. So that means that 2x squared plus 5x minus 3 is 2x minus 1 times x plus 3. And now we can cancel out the 2x minus 1s. So this is the limit as x approaches 1/2 of x plus 3 over 3x minus 2. And now, to be able to use the quotient theorem of limits, is this denominator equal to 0 when x equals 1/2? 3 halves minus 2 is not equal to 0. And now that we have a situation where the denominator does not become 0, so it doesn't become undefined, we can use the rational equation theorem of limits, which says that the limit as x approaches a of some rational function q of x, where q of x is a quotient of polynomials like f of x over g of x. As long as g of x is not equal to 0 at x equals a, we can say that this is equal to q of a. So we can just plug in 1/2 instead of breaking this down any further. So plugging in 1/2 into this ultimately gives -7, which is the answer. This problem says prove that the limit as x approaches 0 of x to the 4th times sine of 1 over the cubed root of x is equal to 0. And if you've been following along this series of tutorials that we haven't seen how to find the limit of transcendental functions. Transcendental functions are non-algebraic functions like sine, log, and exponential. So an important, you might say critical, theorem is called the squeeze theorem, which is this. This is a theorem. Say you have a function f of x, which is very complicated to figure out. But you know that f of x is always greater than or equal to some other function, g of x. So g of x is always less than or equal to f of x for a given value of x. And f of x is always less than or equal to h of x for some value of x. If this is true, and also if you know that the limit as x approaches some value c of g of x is equal to some value L. So the limit as x approaches c of g of x is L. And also the limit as x approaches c of h of x is also equal to L. Then you can make the conclusion, because this approaches L, and this also approaches L, and this is always between them, then you can conclude without having to figure out exactly, explicitly, the limit as x approaches c of f of x will also be equal to L. Graphically, you can look at it like this. Let's say this is g of x. And let's say this is h of x. And they both approach that value as the limit. Well, if f of x is always greater than g of x and always less than h of x, and it has some difficult to evaluate function, by the squeeze theorem, we know that at that point its limit must be equal to L, right here. The proof of this is quite detailed, but it intuitively makes sense. But like I said, I recommend you look at the proof. Ideally, eventually go through the proof. So this is useful because this is a very hard function to explicitly figure out the limit to. So we're going to use the squeeze theorem in this, but now you have to use some creativity and figure out. We're actually going to use let f of x equal the whole thing, x to the fourth times sine of 1 over cube root of x. Now, try to pause the video and think about what you know about the sine function. Can you figure out some g of x and h of x that are a lot simpler to manipulate, such that f of x, such that for all x, g of x is less than or equal to this f of x, which is less than or equal to h of x? Can you think of some simpler functions, some g of x that is always less? Think about that for a moment. Now, if you've seen in trigonometry, you know that the sine function looks like this. Let's talk about a sine. Let's say that A is on the x-axis. We can call it the a-axis. This function, sine A, is never less than -1, and it's also never greater than +1. This function, sine of A, or if you want to say sine of x, the sine function is bounded from below by -1 and bounded from above by +1. Now, that means that this part will never be less than -1 or greater than 1 for any x. Now, given that, can you come up with any, let's say that's f to the 4th times sine of 1 over cube root of x. Can you think of some trivially easy? Now remember, let's leave the x4 and x to the 4th right here, because fortunately, very fortunately, x to the 4th is always greater than or equal to 0. So it's always going to be a positive number. So if this is always between -1 and 1, can't you just do this? Let's try that. So now if you can find the limit of this as x approaches 0, what is it? What is the limit as x approaches 0 of -x to the 4th? Now, negative is the same as -1, right? And that's a constant. So by the theorem that you can pull a constant out of a limit, you have minus limit x approaches 0 of x to the 4th. You can consider this function, x to the 4th, basically a polynomial function. And do you remember the polynomial limit theorem? That we can plug in the value. So this is negative. But if you plug in 0 into x to the 4th, it's just 0, -0, 0, right? So the limit of -x to the 4th as x approaches 0 is 0. Now, let's do the limit as x approaches 0 of x to the fourth times 1, or just x to the fourth. Once again, this is a very simple polynomial, and because the polynomial theorem of limits, we can just plug in 0. 0 to the fourth is 0. And here we go. Here's the squeeze theorem at work. The lower bound limiting function is 0. The limit is 0. The upper limit is 0. And this function limit is between 0 and 0, so it must be at 0. So you proved that by finding a lower bound and an upper bound function that was easier to solve, and you found that they have the same limit, and therefore by the squeeze theorem it has the same limit. Squeeze theorem is a very useful theorem to use in solving difficult limits.